want to start by basically thanking Ms. Martel and Dr. Haas for excellent talks. It actually sets the stage for what I would transmit to you in my presentation. So the first thing that I'll go with is the intent of my presentation is to just share with you how collaborations with industry can actually produce good things for us academics. So I'm hoping most of the crowds in here is academics, but also if you're an industry practitioner, you can play a significantly positive role in making a lot of this happen. The thesis of this presentation is that, construction is an applied discipline. We are the most applied of any engineering discipline. Engineering is an applied science, so we're the applied of the applied. Unless we work with those people who apply themselves, it makes it very difficult for us to produce meaningful research for the industry. And most people believe that if we spend quite a bit of time trying to figure out how the industry works and all this, it takes away from our academic achievements and the awards and all those things that Muhammad kindly mentioned happened because of collaborations with industry. So I'm saying that this is a good thing for us to do. So here's the outline. Essentially, it's not a framework. I'm just going to give you a little bit of some of the ingredients that I think I discovered by talking to my colleagues and all this about how collaborations work. What are the essential ingredients for all these collaborations to work properly? The second part is I'm just going to take you on a kind of like a memory lane, a research journey and development of some simulation tools, which were the basics of what I've done over the past 30 years. So I'll divide that into 10-year segments and show that people like those in academia that sustain specific research topics and advance it as they go on and work with industry on it can actually leave a lot of impact, which would be the third topic. I'll just pick 3 different applications that I thought in industry, they made meaningful difference from different angles. So we'll talk a little bit about that. And finally, conclude with actually the true success of a lot of the stuff that I've done is here. You could see my colleagues and those here and not here today in building the whole School of Construction and the Construction Innovation Center. I think this is more important than all the simulation work that I've done over the years. So let's begin with this, but before I get with the collaboration framework, this is not a template for everyone to follow. I am just sharing with you what I discovered. There's a lot of good ways of doing a lot of things. Industry can lead collaborations. Associations can lead collaborations. Construction Industry Institute, for example, is an incredible organization that made a lot of things happen in terms of collaborations between universities and industry academics. But you can look around and talk to many people over here, mostly those that have some gray hair or a lot of gray hair. They have different ways of collaborating with companies. This by no means is the only way. Just sharing with you what I have learned over the years. So the first and most important thing, in my opinion, is finding champions in industry. And champions could be companies, organizations, or individuals, hopefully a combination of both. I found champions who were in municipal type of organizations, in government. I also find champions in private companies, and I found champions who are individuals within companies, and that was significantly important. So that's the first and most important ingredient, in my opinion, for collaborations to work. You can't find the champions, you can't identify them, things won't work well. The second part is long-term view for whatever one is doing. If we try to be, I tried not to be a butterfly researcher where I just jump into whatever is the interesting topic of the moment. And we in construction are vulnerable to that because we take a lot of applications that exist in computing, in robotics, in advanced technologies of all sorts, materials and all that. And those keep changing at a fast pace. And we have a tendency of jumping in from one to the other. So it may work for some. For me, it's very important what you heard from Carl. He spent his career working on robotics. That doesn't mean that that's all he did. He's an expert on a lot of the construction management stuff, and a lot of his contributions are in those. But there is a thread that sustained him over time. And long-term view with industry is also important. You'll see some of the companies I worked with are still working with my colleagues today, 30 years later. That means they find value. That means we created that long-term mission for all of us. Third element is balance. Industry doesn't have the same attention span. Well, not attention span, the same view of impact as academics do. We tend to gear a lot of our attention over a student. So a student takes, maybe if they're a master's student, a couple of years to produce a thesis, PhD, maybe 5 years to produce a thesis, and we have that long term. But for industry, the project, wonderful project that you heard of, is already done by that. You can't just wait until that happens. So it has to be, focused. It has to be immediate in terms of return. So the balance is important. Create academic contributions is good, but you have to have applied things that industry can find immediate use for. I was able to balance those, and I'll show some examples. Students are probably a very important ingredient. Some of them are here today, and I was very impressed with all the folks that I watched over yesterday. If you have the right students, a lot of good things happen. And finally, creating a culture of collaboration rather than just one-off. So collaboration basics, in my view, there are two ways that you can identify those. You could go purposefully go in and look in and identify pulling people to collaborate with, or you can capitalize on opportunities as they come up. So in my approach, you'd see that what I've done is over the years, I've created purposeful identification. When I started at U Alberta, not very many people, not even my colleagues know, I spent the first about a summer, which was about 4 months long, visiting companies and trying to identify who I'm going to work with. I determined 30 years ago that I'm going to work with industry. And they hired me because they wanted me to work with industry, and that's what I did. So over a summer, I interviewed, visited, people helped me, Bill and Peter helped me, got there, opened doors, got stuff, but I interviewed over 30 different companies, and out of those, I landed on about 5 or 6 of them that I was going to work with. And I defined them basically based on their interest and things I could do which could make a difference in their world, as well as the opportunity for championships. But the other part of it was I also capitalized on opportunities that came about. Opportunities span from different ways. This has nothing to do with construction, but there was a mine planning going on in Syncrude, the Aurora mine, and they needed somebody that does simulation, and they figured, well, here's a guy that does simulation. I had nothing to do with mining. They were asked me, and I was like scared of doing a project. It was a consulting opportunity, and I said, well, I'm not sure. I'll try it. And so I took a chance, jumped in. It established collaboration, introduced me to a lot of the earth-moving contractors that were working with Syncrude at the time. And that started collaborations for a long period of time. And the list goes on and on. The Elmendorf facility and the Rossdale tunnels were basically projects that went wrong, and there was claims associated with them, and somebody approached me to work with them on these claims, and off I took. The key with all of these that you see 6 listed, all of them, after doing some basic work, mainly consulting work with them, I ended up inviting them into my research program, and they're still supporting our activities today. So long-term commitment, I mentioned that a little bit, but you can see I started my work back in 1993 on simulation, and it's still going on. I'm hoping for the next few years, at least, with me involved, but my colleagues are continuing that journey. And the diagram that you see at the bottom is academic research versus industry horizon, and basically the intersection is the sweet spot. So let's talk a little bit about the journey. So solving industry problems with simulation tools was what I started with. This was my ticket to collaboration. What is it that I'm offering to construction companies? Construction companies knew a lot more than I did. I was a professor and full of myself thinking, well, I already graduated with a PhD, so I know everything. And I was humbled very quickly on the first project that I was in. I did not know exactly the methods, the processes, the approach that they were using. Being humbled, I had to provide something that they would probably find useful for them. And it was simulation tools because that was my area of expertise. So offer them that. Why is that? Well, basically it helps them estimate productivity and play around. So simulation is a wonderful tool because you can model things and then you can play with them. And once you play with them, you can get answers. My call in the area of simulation was process interaction modeling, which basically models processes, allows me to model productivity, allows me to derive uncertainty. So if you're concerned about the amount of time it's going to take, you're not sure about it, not sure about the cost, I can help you. I can model the process. Well, I have a CPM network. Well, that doesn't work because it's static. It's not going to give you what you want. It doesn't include the interactions, unexpected things happening. Here, I can include a lot of those, and that you would see in the one that you were at the upper right side. My earlier work was in SLAM 2, which is a commercial product that you could use for modeling simulation systems. Industry was happy with the answers, but then they would ask me another question, and it will take me about maybe a month before I can create the model and come back with the answer. That was not working. So there was opportunities to do things differently. And that is when we started doing some interesting work that industry was likely to use. Instead of me giving them the answers, they can take the tool and apply it. So we'd see Cruiser over here was basically have nothing to do with process interaction modeling. It was crushing operation. And a crushing operation, you can model the aggregate production, but you want to be able to figure out how to change a lot of this so you can get what you want, you can optimize what you want, get the product that you want. We programmed a lot of that. We put it in this environment. It's a simulation environment, but it's a static one. The dewatering was also another problem with one of the companies that was always interested in. So you could see within that, we would model the site and be able to put where the wells are going to be, what the pumps are going to be, solve a set of differential equations, and be able to tell them, well, this is going to be the water table once you've done that. These are not really that interesting for me as an academic, but they were interested for industry, and we were able to do a lot of that. The earth moving operation started, and it continues even today. But research continues to evolve. So what we've done with that is start working with modeling construction environments instead. Instead of using those tools, the tools that I showed you before, typically will take about 6 months to program, some of them a year, to create the programs and the tools for industry. It was very expensive to do, and when they wanted changes, the change will require weeks or months of programming and coding. Very expensive, not really useful. So we had to look, and one of the things that we were able to locate, and that's what good researchers will end up doing, we located a concept in computer science called application frameworks for programming. And the application framework, instead of us developing a program from scratch using whatever language at the time. It was C++, later on C#. Instead of doing that, we developed the framework, and the framework will allow people to actually use it to develop the tools. So we were able to get, this is part of the framework. You can model as a programmer things with this set of tools, as well as some writing minor code, and it produces tools which industry would use that are similar to the other one. So that's quick. I could easily, within hours, produce what is needed. Breakthrough in terms of how we did a lot of the stuff. It created a concept called special purpose simulation modeling, which brought quite a bit of good support for what we were trying to do and what we were trying to accomplish. Well, research needs to adapt and continually improve. The works we've done on the special purpose modeling took us, a while. So 10 years of good production with industry, good results, and a lot of tools all over the place. Moved into the third phase, this is the second phase, the second 10 years of the work. It wasn't enough to model things the way we were modeling them. We wanted to be able to create opportunities where many other things could happen. Real-time input, so that we can figure out how these models change in real time once new data comes into the system, or new information comes into the system, or new weather patterns operate. What impact does it do? How do we do that? We also wanted to create opportunities where different types of players could participate in developing their own pieces of simulation and adding it to the overall basic model. This became an interesting problem that we ended up solving by looking again for what is available. There was something called the high-level architecture that we went into, developed by the Department of Defense in the US for modeling all kinds of war games and the like, very complex operations. But it became an IEEE standard, and we were able to tag into that, figure out how it works, and started developing our own systems using the high-level architecture. The basic concept of a high-level architecture is I can model a big project like the destruction of that bridge as one unit, but it's called a federation. But the federation could have multiple federates. One of the federates could be flow of the river, because it may change different things, and I may want to protect the fish and different events or avoid from flooding. But those could be modeled by somebody else. I can model the bridge deconstruction using my tools, but then somebody else could model the flow within the river. Somebody else could model the trucking of that material to the site and plug in to those operations. These are called federates that are pulled together. To make this work, we have a runtime infrastructure. The runtime infrastructure organizes all these federates and make them work. It's a little bit more complicated than what I just described, but this is 10 years worth of work that yielded some really good results being applied by different companies. The one you see on the far right is one of the last applications developed with PCL, which I'll come to in a minute. Well, all that happened, and now we are into a new phase, leaping into the future. We learned a lot about the federated approach for simulation, but we didn't really get it to the level that we wanted. So this last phase started a couple of years ago, and it's way more complicated to bring a lot of these applications to industry. So doing what a good manager normally does and being more senior, I handed it over to my colleagues and said, this is your problem. So you'll see them around. I see Farouk around here, and Vicente and Gang and others. They are charged with taking this. It's way beyond one person. So we have multiple players doing all this. This would be in few years' time, the results will take place. A lot of digital twinning going on with a lot of what we do. But we've learned also that I was told that the high-level architecture is too complicated to do. Let's use some commercial software. So what do you think would be commercial software? Well, you'd look at the companies like NVIDIA. Omniverse, if you heard of it, is an incredible toolkit. You look at Unity, game engines and the like. You have Simulink and all those. The problem with these, in my opinion, is that same thing that we've seen when I started with SLAM and moved to develop our own tools. First, they are very expensive, very difficult to learn. They won't be applied by industry. They require dedicated resources to develop. They are not responsive enough to solve the problems that we need. So we need to take a lot of these, digest them, understand them, learn from them, and map them into something that we can actually apply to serve the industry problems that we face. Similar to what we did before, just a little bit more complicated. Well, a lot more complicated. So that's where the journey sits right now. Let me show you a little bit of some examples of those long-term collaborations. Wayward Steel Fabricators, a company I started with, these are the list of projects that went on, and I stopped at 2017 because the company was bought out at 2017. They made good money, but their owners still support us in different ways. But you see in these projects a journey that started in 1996 and it kept going. The company sees value. The company gets responsive stuff. And you'd wonder how we started with Wayward Steel. I started with Wayward Steel because they asked me to help them with a claim they were doing in Alaska. From Alberta to Alaska. They were stuck in a major claim, and it will happen to be delivery of steel on time. Things complicated. I won't go through the details, but it turned out to be a logistics problem. And it turned out it's not Wayward's fault. And they were up against the U.S. Army Corps of Engineers, which is armed with a lot of good lawyers. And the general contractor was Mortensen, who Dr. Hanna would know very well. And they're fairly well equipped and deep pockets. So Wayward Steel at the time was doing about $50 million worth of revenue per year. Not a big contractor. They got this job to supply steel to Elmendorf in Alaska, which is one of the largest hospitals the U.S. Army was building. They won the contract because of their specialty and because of their proximity to Alaska shipping. So long story short is they were in trouble, but I was able to come and help them by building models and showing the U.S. Army folks, lawyers, that look, this is not their fault, it's somebody else's fault, so look elsewhere. What ended up happening is they liked the story and negotiated a side deal with Wayward and say, look, Wayward was going to go bankrupt if they lost the claim. They negotiated with them to be on their side because they were convinced of the material we provided, took them on their side and ran with the project. Since then, we started doing projects with Wayward. I said, you can't get yourself in trouble. You need researchers. You don't need consultants. You need to develop tools that basically help you do things a little bit better, have the records, have the information and all that. And that was the journey with Wayward Steel. We did a lot of things, but of course, I pushed on them some simulation work. So a lot of the stuff that we did was steelworks and fieldworks and all that, systems that have nothing to do with simulation. But during the process, you could see the simulation concepts we applied, looking at their operation. Said, look, we can improve a lot of what you're doing, your bottom line, by just looking at the shop, looking at optimizing your operation in the yard and how you provide the material when you need it. That saved them money, helped them big time. The second one is PCL Constructors, and PCL is a company that is a big conglomerate. They are the largest contractor in the country. Well, Elliston would dispute that because they're not really necessarily a general contractor. They are a construction manager and a general contractor, but by revenue, they do about $10 billion, maybe $12 billion annually of construction. So PCL was not going to be interested in what I'm doing because their own construction services group had many PhDs and had many experienced folks. So the selling point to PCL construction is you may not need what we're doing in terms of technologies, but let us help you produce a next generation set of employees that you can hire. So the HQPs, the high quality personnel production, was the selling point with PCL. They liked it. Of course, when we got in, we started producing those good, well-trained people because they worked on research projects. So they had to find them research projects to get them trained with them. And from those research projects, we produce a lot of stuff. PCL ended up being one of the most users of our technologies. The difference between them and Wayward is they take the concepts and whatever we develop, and they take it on their own and developed it and deployed it. You'll see within those a lot of embedded simulations. This one, which is a little bit ugly, but these are cranes moving on site, mobile cranes moving on site for industrial construction. Few million dollars, when these things happen on a major petrochemical plant construction. And any savings in terms of not moving the cranes will save significant amounts of money. They save tons of money because of the models we created, simulation models. They use them in the background to plan and organize and then deploy the best possible locations for those. That helped them save quite a bit of money. And on the top, where you see some neural networks and stuff, they were not really interested in a lot of the research on early on, but by looking at their data, we showed them that actually they're not as accurate in estimating their productivity that Carl talked about as they think they are. They have some really good experts, but we showed them through simple statistical analysis of all the data that basically what they use as the basis for estimating their productivity for formwork, which is bread and butter for them, was random. You could pick a random number within a certain range from the means manual and be as good as their estimate. And we helped them improve that by showing them how to do things a little bit differently. Made a big difference. They took the tools and they implement them. The last example, and these are only three of hundreds, but this one is unique because tunnel construction was an area I had no knowledge, no basis in. I had to learn it from scratch. One of the key things is I took it on myself with all of these applications that I mentioned. It's not easy for academics because we learn a lot of things, from books. And right now you can actually ask ChatGPT and it will tell you how things are constructed. Not sure if it's always right, but we can get that. And it would be sufficient to do your research and publish the paper, because the paper is only 20 pages long and you don't have to explain in detail. But try to execute that project and see how difficult it is. Tunnel construction was one of these, but I spent a lot of time learning tunnel construction and developed into an expert in the area. I knew the ins and outs of all of that, developed a lot of advanced tools for tunnel construction that is still in use today. The innovations can also plant the seeds for different types of startups. So it's not just doing consulting work, doing research which is applied and all this. These can spawn a lot of good, I would say, startup companies. SMA Consulting that Muhammad mentioned early on, is a company that is just focused on doing exactly what I explained, which is basically selling high-end services, not duplicating the consulting work that Stantec does, for example, or SNC does, but it does higher-end services that Stantec and SNC don't have and will need to develop the projects better. So that's what we do within that. The company has grown into just under 40 employees. All of them have either masters or PhDs in the areas of construction engineering and management. Draxware was a software development company, and it went into logistics, and it was sold to a company that does logistics plannings for mine operations and remote construction projects. There are others that you'll see, roots that in our research program. Dr. Hussein worked quite a bit with Landmark, and out of that work, that learning from all that stuff, they built new technologies. AccuBuilt is similar to what Carl showed you on the timber production. They automated a lot of that, but that started within our program with Dr. Al-Hussein and his team. They advanced this now to Promise Robotics, which does the same concept, but using robots instead. And again, they would not, most of their people graduates from the programs that we have at our university. And finally, Dr. Hussein is tinkering with some additional ones. I visited with him. Perfect one with the precast. So success, building the whole school of construction takes time. It started in 1985 before me. Weir and Dozy were the two people that hired me in 1990. And then you could see the group as it's growing over time. The staff, which is on the right side, are still with us or working in companies that we started. But you could see that, you know, this is where things are today. Produced a lot of students. Those are the ones I had permission to use their faces in the application, but there's hundreds of students that were graduated. And out of that came the Construction Innovation Center that takes what I did from collaboration and makes it more like a factory production. That was a mom and pop type of shop where one person was responsible, got a lot of colleagues, got lucky, did a lot of stuff. This is the factory type that will create a lot more collaborations. The CIC Construction Innovation Center is funded by a number of companies, dozens of companies. They put the money in. It is managed by our researchers. Dr. Yasser Muhammad is the current director of that. And it does a lot of work. Those were listed in part by Carl. But you will see we're doing a lot of the work that they would need. Anas is around here. He developed this chart working with the strategic plan for the CIC. Feel free to connect with him and see. So with that, I go back to the first slide. The win-win collaboration framework basically is focused on seeking champions, making sure that those champions are involved in doing what needs to be done. None of this would have happened if I did not really have champions in industry that I showed in one of the slides. And none of them would have happened if there wasn't champions within companies. Wayward Steel, PCL, North American Construction Group, Ledcor, those companies played a significant role in terms of starting all that. Long-term thinking, important ingredient, maintaining balance, involving students, obviously, and creating the culture of collaboration. And finally, I added using research identity for credibility. My credibility came from focusing my work on, I'm an expert in simulation modeling, but I made a lot of this happen because I did all the basic construction management that we all do. The credibility comes from knowing something that nobody else can contribute to, especially in industry that I can add value to. But we're all smart and we could do a good job once given the opportunity. So with that, I would conclude my presentation. Thank you for being here. I'll take a question if Mohammed.